Greetings everyone, Professor Simon here, ready to bring you into that next unit of Calculus 1. Now that we've finished with all of the derivative applications that we're going to cover, it's now time to turn the table around and talk about the opposite of derivatives. We're going to start with the name antiderivative. Okay, and I know that's not very original, opposite of derivative, antiderivatives. It's to not have too many words flying at you at one time, really, is the whole point. And so that we can have something descriptive to call it. Okay, so the idea here is that you will start with some sort of function, and it will be called the derivative, and then you'll be asked to find the original function that derivative function came from, right? So if I start with dy over dx is equal to the derivative of some function, I'm supposed to find the original y equal to whatever that function is. Now here's the thing. If you just keep with me for a second and think about what is the derivative of x squared. It would be 2x, right? What would be the derivative of x squared plus 1? It would still be 2x. What about the derivative of x squared plus 5, x squared plus 10, x squared plus 100? Every single one of those would have a derivative of 2x. So then flip it around like we're doing here, and let's say I asked you, hey, my derivative is 2x. What's the original function that I had? You'd be like, it could be x squared. It could be x squared plus 1, it could be x squared plus 10, it could be x squared plus 20. We don't know, because at some point when you took a derivative, any of the numbers got zeroed out. So when you do the antiderivative, you have to think ahead and be like, well, I know that I could do the x squared part, that's no problem. But there could have been a number there, so we always put plus a constant. Every time you do an antiderivative, you're going to put plus c, plus a constant. Every time you do an antiderivative, plus c. Okay? So, some other symbols that come up while doing this to make this more of an action that you can perform. We have this swirly looking, really stretched out s. That's the integral symbol. The integral symbol symbolizes doing an antiderivative. So when I draw this integral symbol on some function, it means that this function is the derivative of something, and this symbol is telling me to go backwards, do the antiderivative of whatever this is to give me the answer function. And don't forget plus c when you do the antiderivative. When you perform this process of finding the antiderivative with the integral symbol, it is called performing an indefinite integral. Okay? So the integral symbol is like the opposite of whenever you see me write d over dx to mean that I'm going to take the derivative of something. This is to take the antiderivative of something. Right? Or we'll just say take the integral. Okay? So the integral symbol means find the antiderivative of something. All right, so all of the derivative rules, the basic ones, are still valid. So we're just going to be using all of them in reverse. Let's get some examples in there. For example, the antiderivative of cosine is sine. And then notice I snuck in a little bit extra on this one particularly here. The cosine, if I have some number times x, you have to divide by that number. Let's think about that for a second. If I were taking the derivative of sine of 5x, remember the chain rule would have that 5 on the outside, 5 sine of 5x. Or 5 cosine, when you take the derivative, 5 cosine of 5x. So when I'm doing the antiderivative, instead of multiplying by the inside number, I'm doing the anti, right? So it'll be dividing by that inside number, okay? For the same reason that you would multiply when you do the derivative, this works as long as it's a number, not some complicated function, okay? Notice this isn't something more complicated with extra powers or radicals or anything. If it's just a number derivative on the inside, the derivative of x here would be a, right? As long as it's just a number on the inside, then this is completely legal to do in the antiderivative. Just divide by that number. Okay? Same thing here, right? Antiderivative of sine would be negative cosine, and I'm dividing by the inside number. E to the x is its own derivative, so it only makes sense that e to the x would also be its own antiderivative. So if I have e to the ax, instead of multiplying by a, which you do when you take a derivative, in doing the antiderivative, I would just divide by the number portion a. Don't forget the plus c. Okay? Now, power rule. Remember, the old power rule for derivatives was you drop the n and multiply and do n minus 1. So we're going to do that same process in the exact reverse, right? Remember, the process for the derivative is to drop and multiply, then subtract. So if we're doing the 180 on this thing, if we're going to do the exact opposite, then the opposite of the subtraction goes first. The opposite of subtraction is to add a power, add 1 to the power, and then divide by the new power. So instead of multiply and subtract, I'm going to do add and then divide, right? It's the exact same power rule. Notice if I were to drop this n plus 1, it would cancel out in doing the derivative, right? N plus 1 over n plus 1, it would give me this back. So here's how you do the antiderivative with a power. You always add the power first, then divide by whatever that new number is. And that works for every exponent. Remember, we already proved the power rule works for whole numbers, right? Negative numbers, fractions. It worked for everything that we applied it to. But this one has one exception. Do not do this anti-power rule, all right? This antiderivative power rule, integral power rule. Don't do it when n is negative 1. That's this case right here. When n is negative 1, x to the negative 1, that's 1 over x. And if you remember, that one was reserved as a special derivative. All right, 1 over x is the derivative of ln of x. Notice the absolute value here. When I'm doing the antiderivative, I'm starting with 1 over x. And 1 over x has no problem with negatives. So when I'm doing the antiderivative, I have to think to myself, he could have handled a negative because division doesn't have a problem with negatives. But logarithms do have a problem with it, so I'm just going to cover myself just in case, right? And I put the absolute value on there just to make sure that the logarithm can handle everything that this piece that we started with can handle, right? So now with this absolute value, ln can handle negative numbers because the absolute value would just get rid of them. Whenever you're doing the antiderivative of 1 over x, you're going to want to put the absolute value inside of your ln. And again, don't forget the plus c. Okay? So you should recognize all of these rules. Every single one of these was a derivative rule that we used at some point. Okay? And it's just in reverse. For example, antiderivative of 1 over square root of 1 minus x squared should give you the arc sine, the inverse sine function, plus c. Antiderivative of 1 over 1 plus x squared, arctangent of x, right? All of those were derivative rules at some point. You've got all of the trig ones, right? Secant times tangent is the derivative of secant. So antiderivative of secant tangent is the secant function. Cosecant squared was the derivative of, negative cosecant squared was the derivative of cotangent. You'll notice the negative is now on this side because I'm doing the antiderivative this way. Okay? But all of these things should look extremely familiar to you. And I'm just using each one of them in reverse. The one that's really new to you should be this power rule, because it's going to feel a little bit different than the derivative power rule. The integral power rule is just the opposite. You just got to get used to the pattern. Okay? We'll get some examples. The properties of the antiderivative follow the same properties that the derivative have. If you have some number times the function, then it's the same thing as if you were to do the antiderivative and then just keep that multiplied number following along. Okay? If you're going to do the antiderivative of the sum of two things, then you can do the antiderivative of each piece and then sum afterwards. It's just like a derivative. Okay? Now also, I know you have gotten used to using product rule, quotient rule, and chain rule with derivatives. Don't worry about those yet, okay? Antiderivatives don't have exactly the same stuff. We will talk about the anti-derivative for chain rule in this course. The next course we talk about the anti-product rule in the more advanced antiderivative chapter, okay? So in this course, we're only going to hit the anti-chain rule, and then we'll also talk about some applications of antiderivatives. There is no anti-quotient rule as of normal structuring. All you really need is the anti-product rule. Okay, and then there's some other advanced antiderivative methods, but much later on. Okay, so make sure you recognize these formats. Okay, get used to seeing the antiderivative symbol, the integral symbol, and we're going to get some examples of how to work these antiderivatives now. All right, let's get some examples going on for these antiderivatives. I've got two different formats here. I've got the format where you're handed something that's labeled as a derivative, and we've got the kind where it just says, here's an integral, find the antiderivative, right? Because that's what the integral symbol tells you to do. So it's the same process either way, but let's do both formats so that you can see how we write them. Here I'm handed f prime of x, right? Okay, so I'm going to find f of x, right? The antiderivative would mean, oh, I'm finding the original function from the derivative. Alrighty. Well, remember, multiplied numbers are along for the ride. So 5, right? In fact, you know what? Let me give myself a little bit more space here. Sorry about that. 5 times the anti-power rule. Add 1 power first, so that's x to the 7. Divide by the new power, over 7. Minus 2 times, here's the x to the 3 power rule. Add 1, divide by the new power, plus 7x, add a power, divide by the new power. Then minus 4. There's no x's. It's actually x to the 0. So go up a power. That's minus 4x. But wait a minute. Are we done? Don't forget, we did an antiderivative. Plus c needs to be in there. Now let's simplify. So right here, I can just rewrite this as f of x is equal to 5/7 x to the 7 minus 2 over 4 is a half, x to the 4th, plus 7 over 2x squared, right? Minus 4x plus c. And there it is. This is my antiderivative. And yeah, I know it's supposed to be a function of x, right? And yet I've still got this other c in there. What you've actually found, technically, is an entire family of curves. And the only thing the c is going to do if you plug in different numbers is it's going to shift it up or down. It's going to be the same shape no matter what. It'll just move it up or move it down. So imagine a shape, and then imagine it just being repeated over and over again at different levels. And you won't know exactly which one is yours unless you get some other information. In a little bit, we'll talk about IVPs, initial value problems. Okay? Those are the ones where you can actually figure out a particular value for C. But we're just being generic right now. In general, this is the antiderivative of that. This is the original function whose derivative would give me that. Okay? All right, here. I see that it wants me to take the antiderivative, and it's this complicated multiplication. We talked about this. We're not doing product rule here, right? So make this as simple a form as possible. All of those basic rules, they're going to come out all over the place. Simplify your structure as much as possible with these rules. So right here, I'm going to multiply this out. Therefore, it gives me this. Integral. I have negative 24 t to the 3. Right? I've also got a minus 8 t to the 3. I've got a plus 4t and a plus 48 t to the 5th. I'm going to combine my like terms. Notice I have not done any calculus yet. So minus 32t to the 3rd plus 4t plus 48t to the 5th dt. Do you notice something different here for just a moment? It's a t, right? Not an x. It's okay because the integral comes packing its own control variable. Kind of like whenever we're doing derivatives and you see dy over dx, and the bottom variable, the dx portion, is the control, the thing that your independent variable was supposed to be, right? Sometimes we'll even write d over dx to symbolize x is the thing that we're taking the derivative with respect to. Same thing with this antiderivative. The integral and the dt, that's like parentheses. The integral symbol is the front, the dt brings up the back and closes it as one operation, and the dt tells you which one is the actual variable you're interested in. If all of these weren't t's and this said dt, all of this would just be numbers. It doesn't matter if it looks like a letter or not, okay? Because this is the variable right here, it tells you, the one that the integral is using. Okay, so regardless, let's get to here. Notice now what I've got is just 3 power rules. I'm going to do the antiderivative here. I'm going to add a new power. That's going to give me negative 32 t to the 4th over 4. Right? Add the power, then divide. Plus 4 t squared over 2. Add 1 plus 1 is 2, then divide the new power. 48 t to the 6th over 6. Don't forget the plus c. Final answer, negative 8 t to the 4th plus 2t squared plus 8 t to the 6th plus c. And there it is. Okay? So power rules, very, very, very important. All right. Up here, it wants me to find the antiderivative. But before I can do that, I don't need it in a quotient stance. I need it written out in a more simple power rule type of thing. So what I'm going to do is I'm going to distribute the x to the 5th underneath each piece. Okay, so g prime is 4x squared over x to the 5th minus 1 over x to the 5th, which I can then simplify to being 4x to the negative 3 minus x to the negative 5. Notice everything is now in a power rule setup. I can go ahead and find my actual g of x function now. Right? It was g prime and g prime. Now I'm doing the antiderivative. So I add a power. That's going to be x to the negative 2. Negative 3 plus 1 is negative 2. Divide by the new power. Okay, minus x is going to be to the negative 4. Negative 5 plus 1 is negative 4. Divide by the new power. Plus c. Final answer, g of x is equal to, I'm going to have negative 2. And x to the negative 2, that's in the bottom. That should be x squared in the bottom. Right? All right, double negative right here gives me a plus. I'm going to have 1 over 4x to the 4, because notice the x would come down to the bottom, right? And then plus c. There's my antiderivative. How are we doing? Right? All right. Next. Just because it's a fraction power doesn't mean it's not a power rule. And remember, radicals, we want to make them into power rules. Okay? And then x to the 5th is already a power. But I don't want this extra product structure with the multiplication. So I'm going to take this x to the 4/3 and I'm going to distribute it into the two other x's there. So then this is equal to integral. I have x to the 4/3 times x to the 1/2 minus x to the 4/3 times x to the 5/1. Right? Dx. Now, of course, when you're multiplying, you have to add the powers when they're the same base, right? So I have to do 4/3 plus 1/2. Okay? So that means I need a common denominator there. 4/3 is the same thing as 8/6 plus, this is going to be 3/6, right? So that's the addition that I'm going to be doing there with the powers. And right here, the common denominator would be 3. So 4/3 plus 15/3 is what I'm going to end up doing there. Okay. So equals integral of x to the 11/6 minus x to the 19/3 dx. Now I'm doing the antiderivative. These are power rules. So I'm just going to add 1 to the power, right? That's going to give me x to the 17/6, right? If I'm adding 1, I'm adding 6/6. So 11 plus 6 is 17. Okay? Divide by the new power. 17/6, like that. Minus, add 1. That's going to be x to the 22/3. Divide by the new power, 22/3. Plus c. Remember, whenever I'm dividing by a fraction, you're going to want to do the reciprocal and multiply. So to make this more simple, it's going to end up being 6/17, x to the 17/6, minus 3/22 times x to the 22/3 plus c. And that's just a cleaner way of writing it, is all it is. And of course, at this point, if you really wanted to, you could factor out the other x or whatever. But typically, we end up leaving it for this. Sometimes it's easier to just plug things in and do things like that. Okay? Now, over here, I've got an exponential added with a power rule, right? With a polynomial. Just because they're different rules doesn't mean I have to do anything different. I can do each one separately like before, right? So my a of x function is going to be e to the 5x is its own antiderivative. So the negative 3 is along for the ride. E to the 5x is his own antiderivative, but there's a 5 in there. So I have to divide by the 5. Remember, if it was a derivative, I would have multiplied by the 5. No. Antiderivative, I divide by the 5. And x to the 6th, I have x to the 7th over 7 plus c. And actually, there's nothing to simplify here. You could write 1 over 7 x to the 7th if you wanted to, or you can leave it like that. Okay? That's an antiderivative of that. The exponential is just its own, right? And just don't forget to divide by any numbers that are up in there. Not added numbers now, mind you. It would have to be a multiplied number like the 5 is. Okay, one more example for this scene. I'm going to do the same thing here that we did over here. I want to distribute the 2x to the third to each piece so that I can try to simplify this into as many individual simple rules as possible. Okay, so this is going to be equal to integral. I have negative 4x to the 7 over 2x to the 3 plus 5x squared over 2x to the 3 dx. This is going to be equal to integral of, I have a negative, 4 over 2 is 2, and 7 minus 3, I have x to the 4th. Okay, cool, no big deal. Plus 5 over 2, and then x to the 2, x to the 3. 2 minus 3 is x to the negative 1 dx. Now look real close and try to remember, are both of these power rules? This one definitely is. But this one, x to the negative 1, remember, that was the one exception. We don't do the power rule on x to the negative 1. Oh, Professor Simon, what if I forget that? It's okay. You'll get reminded real quick. Because what's negative 1 plus 1 to do the power rule? It would be 0. And then you would try to divide by 0. No go. Right? So as soon as you see x to the negative 1, you got to remember, hey, wait a minute. X to the negative 1, no, that's really 1 over x, right? This is 5 over 2 times 1 over x. And the antiderivative of 1 over x is not a power rule. Okay? So here, I'm going to do my power rule. I'm going to have, let me do it over here. I'm going to have x to the 5th is my new power. So I have negative 2 over 5, x to the 5th. 4, I add the power, right? 4 plus 1 gives me 5. Divide by the new power. Plus 5 over 2 is along for the ride. And then antiderivative of 1 over x is ln absolute value of x. Don't forget the absolute value. When you're doing the antiderivative, you get that absolute value. Plus c. And here's my antiderivative. We're not done yet. More examples. Let's do some trig and some physics. So, antiderivative of 3 cosine of 5x minus 6 sine of 2x. So here we go. I'm going to do the antiderivative of cosine, which is sine, right? So equals 3 sine of 5x. Now remember, if there's a number inside, you got to divide by it. Boom. Next, minus 6. Antiderivative of sine is negative cosine. So double negative makes it a plus. Cosine of 2x. Divide by the inside number, which is 2. Don't forget your plus c. And one little simplification, right? 6 over 2. I can simplify that to 3. Done. Okay. Over here, f prime of x is negative 2 over 1 plus x squared. That does look a little familiar, doesn't it? I remember seeing the over 1 plus x squared. Maybe that negative 2 is just a multiplied number. If it is, then I should be able to just do this. Negative 2 times 1 over, right? And there it is, right? If it's negative 2 times that, the antiderivative of 1 over 1 plus x squared was arctangent, right? And then I just have a negative 2 multiplied with it. So my original function f of x is just going to be negative 2 arctangent of x plus c. Right? Remember, you can write tan inverse, tan with a negative 1, or you can write arctangent. They are synonymous for the mathematics that we are doing. All right. Here's another one right here that goes along with that same pattern. I'm noticing that I recognize the square root in the denominator with the something minus x squared, but it doesn't look quite right, so I need to do a little bit of rearrangement. I can factor that 12 out, right? That would be 12 times 1 minus x squared. Oh, look, there's the piece that I need. And since it's in a square root, I can actually split that because it's multiplication. So it would be square root of 12 and square root of 1 minus x squared. Okay. Well, another thing. The square root of 12 is just a multiplied number in the bottom, and the negative 8 is just a multiplied number in the top. And remember, with antiderivatives, I can just pull those numbers out of the way and bring them along for the ride. So then this would be equal to negative 8 over square root of 12 times the antiderivative of 1 over square root of 1 minus x squared dx. Look, there's that function right there. We recognize that one. That's the inverse sine function. Well, I can simplify this negative 8 over square root of 12 also. Don't forget, square root of 12, I can actually write as 2 square root of 3 instead, because 12 is 4 times 3. And I can actually reduce that sum, right? I can get negative 4 over square root of 3, and then this would be arc sine of x plus c. Alternate here. Don't forget that we also had a derivative rule for inverse cosine, for arc cosine, and it was the same exact thing, but just with a negative in front of it. So if I wanted to just absorb the negative and keep the negative in the integral here instead, I could have gotten this other answer, or just 4 over square root of 3 arc cosine of x. Either one would work. Just make sure you keep track of your SIGNs, right? Okay, let's hit the physics one right here. Acceleration is given as some function of t, not x, function of time, right? Well, okay, remember we defined back in derivatives, acceleration was the second derivative of position, and velocity was the first derivative of position, which means acceleration was the derivative of velocity, right? It keeps going, like derivative, derivative. Well, we're doing antiderivatives now, right? So I can actually do a couple of antiderivatives here to get from acceleration all the way to position if I need to. Let's do it generically here. I don't have an initial value problem. It's not an IVP yet. I don't know anything about starting velocities or starting positions. So I'm going to have to keep it generic. But I'm not just going to put plus C's for these, okay, because it is not that generic. Watch. I'm going to do the antiderivative here, okay? So basically, I'm going to be doing A of t is equal to V prime of t. You could also say V dot. Remember, we also said that that was one of the symbols. V dot was a derivative of time. Okay, so velocity V of t is going to be equal to negative 32 times t, because it's just a number, right? T to the 0, If I do an antiderivative, I get t to the 1 divided by 1. So it's just that. It's supposed to be plus a constant, right? But I'm not using c. Instead, I'm going to use the physics terminology v naught. That means beginning velocity, v sub 0, okay, not the fighter, v naught, v with a subscript of 0, okay? Now, this is the velocity function in general until I get more information to figure out what the beginning of velocity was, okay? Velocity is the derivative of position, right? So for the position function, I'll use p of t for now. Some people use s of t. Some people use h if it happens to be a height off of the ground. That works too. I'll use p right now just for alliteration here. So that means this is equal to p prime of t, right? Or p dot, right? We use dots sometimes. So I'm going to do the antiderivative here. That's going to give me negative 32 over 2t squared. Because remember, I add 1 to the power and divide by the new power. Plus v naught times t. Look, v naught is a number. It's something. And just like before, when you do an antiderivative of a number, you get it times t. So antiderivative of some number is v naught times t. But I still need another constant. I did another antiderivative, so I should be putting plus a c, another constant over here, right? Well, I want to use something more meaningful. In this case, it's going to be p naught, whatever the initial position was, okay? And the reason why I can name these things like this instead of just some plus a constant, these things that we're putting in, when you plug in 0, these zero out, right? So if I were looking for the initial velocity, in other words, when time is 0, that's exactly what would be left over, that number, whatever v naught is. And same thing here, right? If t were 0, the initial position would be the only thing that's left over, okay? So that's why I'm labeling these things the way that they are. And of course right here, 32 over 2, I can simplify that, can't I? That would be negative 16 t squared. Now, hopefully at some point you've seen a function or a formula that looks just like this, okay? This is one of your beginning physics interaction formulas for kinematic motion with an initial position and an initial velocity from free fall, basically, right? The negative 32 represents the pulling acceleration of gravity in feet per second. And then, of course, you have your velocity, which would be some result of how you started mixed with the gravity. And then this would be the position of that velocity mixed with the gravity, right? Okay, but it doesn't matter. Even if I wasn't doing free motion and gravity, I could have some acceleration function, whatever it is. One antiderivative would get you to the velocity function of time, and another antiderivative would get you then to the position function of time. Okay, now I need you to realize that even though we've been doing derivatives all this time, that's really just been a buildup. In reality, in real physics, we never start off with a position function. It's very difficult to create a position function. It's actually a lot easier to measure velocities and accelerations due to some change. So real physics, a lot of times we start with either an acceleration or a velocity, and then we build with an antiderivative from there. Okay? All right, one more example here. Something with some trig fun in it. Integral of 1 over 1 plus sine theta d theta, right? It's okay to have theta here because theta is my control variable in the integral. Great. I don't want something that's set up like a quotient rule though, do I? No quotients. So I have to find a way to fix this so that it can be some separate trig pieces that I can integrate with those simple rules. Alrighty. So let's see here. What I'm going to do is I'm going to multiply by the conjugate. I'm going to multiply this denominator by 1 minus sine theta. But of course, if I multiply here, I'm going to have to also multiply that same bit there, right? So let's see what we get when we do that. This is going to be equal to integral 1 minus sine theta over, and whenever you multiply out conjugates, don't forget, that gives you a difference of squares. So I have 1 minus sine squared theta, d theta, like that. But wait, 1 minus sine squared theta, that's a famous trig identity, right? Sine squared theta plus cosine squared theta is equal to 1. So 1 minus sine squared theta is cosine squared theta. And this is actually very, very good. I know it seems not because we still have the square in there, but now that it's a single term, one piece in the denominator, I can easily distribute it to each of these pieces and make it two separate fractions that I can simplify much easier. So then I have the antiderivative integral of 1 over cosine squared theta minus sine over cosine squared theta. 1 over cosine squared is secant squared. I hope you're getting excited about that one. That's one of our antiderivative rules, right? Now right here, sine theta over cosine squared theta, what I'm going to momentarily do is split this as a multiplication into 1 over cosine theta times sine theta over cosine theta. Notice that this is the same thing as that, right? I just kind of unmultiplied it a little bit. And the reason why I did that is because I knew sine over cosine would give me tangent theta. And then whatever's left over, I can just try to work with. Well, it turns out 1 over cosine is secant. And what I have is secant theta, tangent theta, d theta. Both of those are basic rules that we can deal with. So my antiderivative here, antiderivative of secant squared theta is tangent theta minus antiderivative of secant tangent is secant theta plus some constant c. All right? Let's sum up this section with a couple of applications of antiderivatives called initial value problems. We'll do a generic one and we'll do a more sort of realistic one, right? Okay, so if I start off with some sort of derivative, second derivative, whatever, and I have some sort of other information about the derivatives and the functions itself, then what that means is I don't have to put just plus c's in the final answer. I'm actually able to figure out a specific function, not just a generic family of them with a generic constant. Okay, so I still need the constant for a moment. Every time you do an antiderivative, you bring in the plus c, but these other pieces of information will allow me to fill in that specific c that makes these other conditions also true. Okay, so let's start with stage one here. I'm starting with a second derivative, and so my first step is to find the first antiderivative, which is going to be f prime, right? Because the first antiderivative is going to move me up one level. Here I've got a power rule, so my x to the 2 becomes x to the 3. Divide by the new power, so I have negative 4/3. Next, I'll have x squared, right? 1 plus 1 is 2. Divide by the new power, 4 divided by 2 is 2. And then plus 1 becomes plus x and plus c, okay? So I've got my first constant here, c. However, I have information about the first derivative, okay? If I didn't have information about the first derivative and say I had two pieces of information about the original function, then I would keep doing my antiderivatives until I got to the place where I could start using the information. In this case, my first bit of information is about the first derivative, and that's where I'm at. So, right here, I'm going to take this and plug it into this function. What that means is all of my x's will become -2, and my output becomes 17. So for a moment, I say 17 equals -4/3 times -2 to the third plus 2 times -2 squared plus -2. And I don't know what c is. That's the whole point of this. I'm trying to figure out what c is. Okay, so let's condense a little. That 17 is equal to, I've got -8 times -4/3. That gives me 32/3. I have 2 times 4 is 8. Minus 2 is another 6 plus c. So let's see. I'm going to have to subtract 6 from both sides, which will give me 11 minus 32/3 is going to be what c is. So that means that c is going to be 33/3 minus 32/3. C is 1/3. Right? Okay, so what this is telling me is I can now take this c equal to 1/3 and I can fill it in to my original derivative function here. So I now can rewrite my derivative function exactly. F prime of x is equal to -4/3 x cubed plus 2x squared plus x plus 1/3. That's what that's telling me now. Okay, well now I continue. I have more information about the original function, so I'm going to continue. The antiderivative now is the function f of x, right? I go to my new power, x to the 4, and I'm going to divide by 4. Well, that will reduce with this. I'm going to get -1/3 x to the 4th. Next, new power is 3. I'm going to divide by that new power. So 2/3 x to the 3. And 1/2 x squared. And 1/3 x. Plus, I'm going to use something else. K. Sure. I just don't want to use c because I kind of already used that in this problem, and I don't want to confuse it. It doesn't matter what you call it, as long as you don't confuse it with something else. It's just some constant. I don't know what it is, right? However, I do know that I can take this piece of information now. F of 1 is supposed to be 5. I can take that piece of information and plug it into this function to make it into the k value that I need. So all of the x's become 1, and the output becomes 5. So 5 equals -1/3 times 1 plus 2/3 times 1 plus 1/2 times 1 plus 1/3 also times 1 plus k. All right, let's see. -1/3 plus 1/3, right? Those go away. And I have 2/3 plus 1/2, and I'm going to be subtracting those to solve for k. So what I have is 5. Let's go ahead and get all common denominators here. 5, and we're going to turn it into sixths. 5 is 36 minus, this is 4/6 minus, this is 3/6. Okay, so that's the 2/3 I subtracted. That's the 1/2 I subtracted. 5 is 30/6, and that's going to be equal to k. So what I'm getting is 23/6 for k here. So my final function, f of x, is equal to negative 1/3 x to the 4th plus 2/3 x to the 3 plus 1/2 x squared plus 1/3 x plus 23/6. And there you have it. That's my original function using the initial value properties. Another option that can come up sometimes, by the way, is instead of giving you derivative information, they'll just give you two function pieces of information. Well, that's fine too. That just means that I would keep doing antiderivatives till I get to this point, but the c would still have been in here. I would have two letters in one function, and then you would just plug in both pieces of information, and it would give you a system of equations that you have to solve is all. You just have to solve for c and k at the same time. There's not much of a difference, just a little bit a different approach, but it doesn't change in the way that you look at the problem, okay? The initial pieces of information are to be plugged into whatever function they cohere to. All right, so one more sort of real world example. I say sort of, Spider-Man. Spider-Man throws Rhino off the top of a building. Now remember, Rhino has really good reflexes. He eventually is going to correct himself and land safely. This is not a violent problem. Spider-Man is only trying to subdue Rhino, keep him from stealing money from people, right? Spider-Man throws Rhino upward off the top of a building. Whee! Right? It's a fun ride. Like, here's the building, right? Spider-Man's throwing Rhino upward, and then Rhino eventually will land on the street on his feet. Okay, so it's doing this. They want you to find out what is Rhino's maximum height. So in other words, how high is this point up here? And how long did it take until Rhino landed safely on the street below? Using the initial velocity, right, of 50 feet per second, and the height of the building as 90 feet as the initial position. We're disregarding that Spider-Man is somewhere between 5 and 6 feet tall, and Rhino's probably, 8,000 feet tall, whatever. We're just going to ignore those things for now. And we're just going to say that the 90 feet is his initial position when Spider-Man is throwing him off of the top of the building. Okay? So, let's start with acceleration. Acceleration due to gravity in feet per second, as we saw in the previous scene, is -32. And that's a constant. We're not taking into account any other acceleration, any other forces other than the constant force of gravity. Of course, Spider-Man put a force on Rhino when he threw him off the top, but we're talking about after that moment. T = 0 is the moment he leaves Spider-Man's hands. Okay? So there's no other forces acting on Rhino other than the downward pull of gravity. However, he does have upward momentum from the throw. So that doesn't mean he's just going to drop, right? He's going to go up some, and then he's going to come back down. So here's my a of t. My first antiderivative will give me v of t, the velocity function, right? Because technically a of t is the second derivative of the position, right? And in this case, by the way, the position is going to be the height off of the ground. That's the foot measurement here, is the height that he is off of the ground. So v of t, the antiderivative, is -32t plus some constant. I'll use v naught. Okay? But I have some initial information. This is an initial value problem. This thing right here, as the initial velocity, is telling me that v of 0 equals 50. That's what that's telling me. V of 0 is 50, right? So if I take that into account, then 50, I'll just do it here. 50 should be equal to -32 times 0 plus v naught. And of course, -32 times 0 is gone because it's times 0. So 50 is equal to the constant v naught. All right, so this tells me that my actual velocity function, okay, is equal to negative 32t plus v naught was equal to 50, right? That's what we just found out. I'm plugging this in to v naught. So I now have the velocity function. I then take the antiderivative of that to get the position and or actual height this time. The height is going to be the antiderivative, which is going to be negative 16t squared. Remember, I go up a power 2 and divide by the new power 2. 32 divided by 2 is 16, negative in this case, plus 50 times t plus the initial height, right? But let's say we didn't know that that's what that was supposed to be. I'm just putting h naught here just to have some constant there. Okay, you could put plus k or plus c or whatever. But notice that what has to happen is I have to decide on some value to start with. Well, that's this. This is telling me right here, okay, that h of 0 is 90. The beginning height at the beginning of the journey, he is 90 feet off of the ground. So that means I would put 90 is equal to negative 16 times 0 squared, 50 times 0 plus the constant. These are 0, and I have 90 is equal to the constant, whatever you called it, and I'm going to plug that in, just like in the initial value problem. So I have my height function, h of t is equal to negative 16t squared plus 50 times t plus 90. All right, so now that I have my two important pieces of information, my two equations, I have my velocity equation, I have my height equation, both of them related to time, I am now ready to answer the question, or the two questions here. So, what is Rhino's maximum height during the flight? Poet didn't know it, right? Well, that's up here, right? At the vertex of his turn, of his flight. Don't forget that that's a horizontal tangent point, right? Well, that means that the derivative of position is 0. Wait a minute, what's derivative of position? Velocity. Oh, yeah. And that should make sense to you, right? Because he had some velocity, right? But gravity's pulling, slowing him down. And then all of a sudden his velocity for just a moment is 0. Then it's still pulling, and he starts coming back down. That point at the top is the moment when velocity is 0. Okay? So what will that do for me? If I set this equal to 0, I'm finding a critical point of the height function because that's the derivative, right? And if it's a critical point, it's going to be the maximum. But it's the t value that I'll be finding. They want to know what is the maximum height. Well, once I figure out the t value, I can plug it back in. Let's do all that. Okay? So here, look. Let's separate this out here. I've got my functions. Now let's use them. Rhino's maximum height. I'm going to find my critical time. My critical time is when the derivative is 0. The time that happens when negative 32t plus 50 is equal to 0. Well, so I'll add the 32t and divide by 32. T is going to be 50 over 32, which reduces to 25 over 16, right? From here, we'll just have to leave it like that for now. This is my critical time. This is the amount of time it takes for Rhino to reach the maximum height, right? Okay. From there, I then say, oh, well, what is h of 25 over 16? Right? That's what I want to figure out. I plug 25 over 16 into this function. That's going to be negative 16, 25 over 16 quantity squared, plus 50 times 25 over 16, plus 90. Right? Okay, I'm going to separate this out to give myself some space for the last question. Alrighty, so now I just need to crunch this. Let's see. That's going to give me 25 squared over 16, negative 25 squared, which is 625, incidentally, over 16, plus 2 times 625 over 16. And I can do that because 50 is 25 times 2, and I just did the 25 times 25. And of course, I know you're punching this in your calculator. You're going with it for that. That's fine. I'm probably eventually going to do that too. But notice what's happening is I'm getting a subtraction here. This is going to subtract and cancel out the 2 there. So what I've really got is 625 divided by 16 plus 90. Saving time here, I'll just crunch that one for us. Right? So 625 over 16 plus 90. Okay, I have 129 feet. Okay? And it happens at 25/16 seconds afterwards. 25 over 16 is 1.56 seconds. So a little bit more than 1.5 seconds after he's thrown in the air, he hits a peak height of 129 feet. Okay? And that comes from the critical point where the velocity is 0, because the velocity is the first derivative. Okay, next. How long until Rhino lands safely on the street below? Well, he starts out at 90 feet up here, right? The street below, we're assuming, would be 0 feet. That just means that I'm going to take my height function and set it equal to 0. Right? So 0 equals negative 16t squared plus 50t plus 90. I don't know, and it doesn't matter how much you like quadratics, that one is not going to be fun to factor. It may not even be factor, probably isn't factorable. You really need the quadratic formula on that one. So t equals negative 50 plus or minus square root. 50 squared is 2,500, right? 5 and 2 zeros. Minus, so plus 4 times 16 is 64 times 90. All over 2 times a is 2 times negative 16 is negative 32. Okay? So from here, let's just crunch, because I'm not going to be able to do that square root by myself anyway. That's going to be a nasty decimal. Okay, so I've got negative 50 plus square root 50 squared 4 times 90. Divide by negative 32. And I'm getting negative 1.27. T is approximately negative 1.28 seconds, or T is approximately, I'll just hit up here and change this to a minus instead, and then divide by negative 32, or T is 4.402, yeah, so 4.4 seconds. Okay, now which one of those makes sense, right? First of all, time can't be negative, right? Just in general, in physics, that's bad form, right? There's no physical interpretation of negative time, and no, it doesn't mean time moving backwards. Negative time has all kinds of bad implications, like how cause and effect can get reversed, having the effect before the cause, and that doesn't make physical sense and things like that. So negative time just isn't even an option. 4.4 seconds positive, though, does make sense. Here's what's actually happening. The math is blind to physics, right? In this case, the math is seeing the entire parabola here, and it's seeing the other side of the parabola of him going basically through the building, if you will, and with negative time, it just doesn't make sense. That's where that other answer is coming from, and it's the one that we can't use. Basically, it's not in our domain, right? So 4.4 seconds is going to be when his height over the ground is 0-ish, right? Okay, so I hope that this has helped you understand what an antiderivative is and how we can use our basic derivative rules in reverse to form the antiderivative basic rules. For the next couple of sections, we are going to be dealing with a lot of different things that seem different, but they're all going to sum up to this kind of thing. We're going to be using antiderivatives to do all of these things that we're going to start talking about next.